I'm going to talk about today is really a project that we did about real-time PFAS measurements using the SIFT-MS. So this was a client request we got. Traditionally, I mean, Element are a stack testing company, test house, things like this. So generally we work to published methods. So we know that there's published methods out there for PFAS. We've seen them in the first presentation. There's obviously other ones now, French, Belgian methods as well. So we knew we could use them, but they give discrete results. So you sample for a period of time, 3 hours, 6 hours, get a result. And a client or several clients that we were working with wanted to know if there was any possibility to see real-time data. As it says up there, they expected some low values, low ppm, even ppb levels. They did have some other organics there, but it was a limited suite. And they ideally wanted this real-time data over several hours. So they wanted to see what was going on in the process. Mentioned the extractor procedure. You know, we could have done several discrete samples, and we did that, albeit not following the OTM methods, using a bit of a simpler method, just impingement into water to see what results they gave. It's probably more linked to the standards that the lab already worked to, using water analysis samples and standards. And then there's obviously a cost to doing those samples, as well as a time element when you take the samples before you can get the results. So we had a SIFT-MS, and so the theory was, you know, that SIFT-MS may see these compounds by identifying fragments, so that it could give real-time data. So the SIFT-MS, for those that don't know, selective ion flow tube mass spec. There's a poster downstairs that probably explains the bits about the SIFT better than I will or can. But briefly, there's a microwave plasma that generates some reagent ions from moist air. I mean, the SIFT that we have just looks at the positive ions, but you can get negative ions as well, which opens it up to a more higher range of instrument compounds that it can detect. So these reagent ions go through a quadrupole mass filter, which selects one of these reagent ions lots of times in a short space of time, goes into the sample inlet where it reacts with the sample gas, and you get a reaction from that. So there's several different reaction mechanisms that I mentioned there. The next slide shows some examples, and then these the product ions then go through to a mass spec for quantification. So just an example of some of the reactions that happen. So you can see on the screen there, sort of H3O plus is one of the reagent ions. If it reacts with acetone, for example, you get a change in the mass of one as the proton's transferred, and you can get dissociative electron transfer. So effectively, we get fragments created. So that's what we sort of saw with the PFAS compounds. So the potential was it can measure organic compounds, very low levels. It can measure ppb at the same time as maybe ppm in other compounds. We knew it could do nitrosamines. They were already in the library. Odorous compounds, we'd used it for some projects on that. So the question was, can it measure PFAS? So the project outline that we wanted to do was check a response with the PFAS standard, see if it would create something, obtain these specific standards for the project that we're looking for. I can't go into too much detail on the specific project because of an NDA that we're working with, but we'll go through the principles. So then we'd scan these standards, see if any reaction products are visible, create library entries for those in the SIFT library, and then we can adjust effectively reaction rates to sort of perform a calibration. So we can make it read what we want it to read for the quantity. And so what we decided to do first when we were doing this was to get some gas bags from site, just to see that when we got a sample of the gas from the site, the SIFT would be able to see this matrix, even if it could see sort of the neat PFAS standards. Run the scans to see approximate levels and what compounds are there, and then we may have to do dilution as well. And then the ultimate aim was to hopefully get the site and do some online measurements. So let's see how we got on. So this isn't one of the ones that we're looking for on this site, but the lab had some octafluorocyclobutane reference material. This is one of the PFAS compounds. It's in the OTM list, so we knew it might be of interest at some point. And so what we initially did was analyse this using a mass scan, so the SIFT can do the same scan, which is like a targeted analysis, or a mass scan where it scans to see what might be there. And we used the sort of the range that the SIFT can look at, which is the 15 to 400 Dalton, and we used all 3 positive reagent ions that we have on our instrument, so just to see what we'd get from that. So it does show some limitations that, you know, once you get above 400 Dalton, we may not be able to use it for all the PFAS compounds out there. So it probably isn't a surprise that I'm stood here talking about this, that it worked. So what we did see with the octafluorobutane, cyclobutane, is that using the O2 plus reagent, that it produced 2 fragment compounds at 131 Daltons, which you can see on a, I haven't picked a very good colour to show these up, but honest, there's some green lines in here. So there's a peak shown at 100, 131 and 200, which is linked to the parent compound. The peaks at the left-hand side here, basically when we run a neat like a fresh air sample or a nitrogen sample or whatever, these are the peaks that would get, these are the reagent ions. So you would always see these, but if we ran just like sort of a baseline sample, you wouldn't see anything beyond these like sort of reagent peaks and maybe some like water vapor linked ones. So these ones shown up here, when we just put that neat reference material in, showed that yes, we can see that. So we knew we could see this PFAS, and the other PFAS that we looked for it responded to as well. So from that, we'll create library entries. So the SIFT library's got, you know, hundreds, if not thousands, of compounds in. So we could create these library references, and going back to this, you can't really see it on there, but there's a ratio that these peaks are showing up, so we can use sort of where the peaks were shown on the mass and the ratios to come up with a library entry for that compound. And then when we put the gas back in at a known value, we can then alter the reaction rate to calibrate it. So if we're doing, so basically